Okay, starting last Monday, so I really start showing the procedure. So this is like a continuation of what I finished up last Monday. So Monday, PF, ultimate goal, as I mentioned, is to compute the probability of the failure. So this we use always transform into the standard normal distribution based on the assumption that X is a normal, then U is a normal. Straight transformation. Then also the author claimed the other, for the case of other, the probability density function situation, it can be done still transforming, still the somehow cast into the independent set. Okay. For the probability density function, originally, of course, is all coupled. Then by assumption of mutually exclusive, then change into the multiplication of a probability density function. That's independent. Then I really looked through quite a few different the papers and all that. Then try to cast into the transforming into the standard normal distribution. Everything, whether it's correlated or not, or whether it's a non-normal probability density function, try to cast back into the standard normal distribution. Otherwise, almost impossible to solve. So make assumption here, make assumption there. So that's what happened. But I'm gonna really, in that area, I'm gonna really put it nicely together and will explain to you. But there are lots of use, as we have done for two random variable case, lots of use for the design application. So it's not just a waste of saying that, oh, this is only good for normal, only good for uncorrelated situation, but that's really beginning. But conceptually, it's very powerful to understand what happened. Then you could, if you're getting into in this area heavily, you can contribute in this field. That's what I feel. Okay, last Monday, this is what we did, and this was cast into the form. This is something like a page 13 in that area, and alpha I and U I star, and the UI star, that's really the MPP point, MPP, most probable MP point. And if I redraw this, is after the transformation. And here is G function. This is origin. So if I if I say this is U star, and the U star, this is really tangent point. So first order reliability method means it's really Taylor series expansion using the first two terms, which is really the equation of a straight line. So which is what this is. So this is as we have done. GU is equal to G, right? U star plus delta GU star and U minus U star. So this is a straight line equation for the Taylor series expansion, keeping the first two terms. And this connected this, and the length you can say is use norm of the U star, or square root U. I think you read, I'm pretty sure, up to the at least MPP surge, which is equal to, right? I is equal to 1 through norm. Or then this is really the beta. The whole idea is if you find the beta, then home free, because PF is equal to, another way to say is minus beta reliability index, okay? So we have the expression for the alpha I. So where this alpha I you have to compute, whether it's a 2 random variable, 3 random variable. So this is the value, then you have to really compute that, which is, I'm going to write here, G delta UI, this is U, evaluated at U star, which is a component of gradient. This is the ith component of gradient G, and this is the square root of I is equal to 1 through N U delta U I U star evaluated at U star at the MP, the point, okay? So so this component here, this component is delta G U is equal to delta G U over del U1 del U2 all the way through U del UN, simply speaking. So among the n component, it shows ith component to define the alpha I. This denominator is nothing but a norm. Square of this term plus square of that term all the way through, then take a square root, which means it's a norm. Okay? The distance. And this component, you have to compute that. So here, So defining A in the handout in the two sets of the file. First set, use a bold character to define the vector. This is a vector. A is a vector. And this guy is a n entry vector. Take a transpose, because this guy has n entry vector, and you have to multiply transpose of that n entry vector, then you will get the summation. So this is a vector defining alpha 1, alpha 2, all the way through the alpha n. So we have a definition. So if you do that, this is equal to, top is back to gradient. This is a gradient G, U star right at MP point over the norm. This is a norm. Right? That's a norm. So it's back to G, U star. And if you look at carefully, the gradient vector, this is a vector, over the norm, magnitude of this entry, then this is equal to unit vector. So this guy is a unit vector. But this is a unit vector, and graphically, if you look at here, right at here, if this is of course original, the performance function transformed into the U space. So if you look at just this curve, right, G, then you take a gradient. What's the direction of the gradient? Always outward direction. Gradient here is that direction. Of course, normal to the tangent. So this is the A vector. This is A vector. That's because that's a gradient. Okay? And now, as you look at the U star, and if you connect from 0 to U star, then think about the vector U star running from O, 0 to here at MPP. This is, we call the MPP. So this is the vector direction opposite to this. By looking at this, this is a vector. So this guy is a vector. I can say U star vector, but you have to get the unit vector, you have to divide by U star. Identical format, right? That's unit vector. Or you can cast as a U star dropping this arrow as B is a scalar quantity beta. By looking at this, comparing this coming from here, which is normal to the tangent, and this guy is coming from this side, which is really normalized U star vector. So I can claim that, I can say that minus A dropping the arrow, which is all vector, n-dimensional vector, is equal to U star over the beta. Very important. This is a very important relation, equation. So from here, then you can say that this is U star is equal to minus A beta. Over here, beta is a scalar quantity, just a number. A is a vector. You can treat as a vector pointing from here to here. Q1, clear? This is one of the really equation you will need to get a solution for first order reliability method. So because this, at the beginning, we don't know the U star, best location point U star, but we have to keep iterate. We'll show you iteration procedure. Iterate, then by setting up the convergence criteria, then you can define the MP point. So that's where we are. I think so far should be clear. Last couple lecture, I didn't do well, but so today I really like to make it really clear, but who knows, well, we'll see. Then this expression back down to that probability of the failure, which is of course is approximation. Why this is approximation? Because it's a first order. G is expressed as first order Taylor series. That's why it's approximation, but it's a very good approximation. And this is phi. We write this guy once again. So writing here, I is equal to 1 through n, and as we wrote is alpha I ui star. So here, this is in the collective sense. This is a single value. Then we develop into n-dimensional vector, which is A. So this UI is of course coming from the U, which is n-dimensional vector, U star. N-dimensional vector is just coming, just the ith entry is what the UI star here. So I'm going to replace replace the summation with the vector multiplication to simplify it. If you do that, this vector multiplication is nothing but the one vector multiplied by transpose of another vector. So I can say this is A times U star transpose. This is A. Will be identical to simplify. Okay, that's what that really means. Around page 13, page 14. So A here is a unit vector pointing this way, opposite to U star, okay? So that's why this is set, I reset to negative A. Why? To change direction to the same direction as to U star beta. Got it? 성태. Okay, so far it's better. And the U star, so we got that. So now here, so I'm going to replace the expression A, U star transpose U star is minus A beta. So it's minus A beta. I'm going to put the transpose right there because beta is scalar. So I'm going to put the negative sign here. So commutative. A times transpose of A is equal to 1, right? Because A is a unit vector. So I can say this guy is equal to phi minus beta. So this is a final destination to get that. It's a very, very nice expression. Everything, whether it's really normal or non-normal probability function, somehow, let's put it that way, somehow cast into the normal, standard normal distribution, then otherwise you can't solve it, too complicated. That's what you will find. I looked through quite a few different journals, and I can say it's a trivial. So this is what the beta is, of course, usually the positive value. And then I can say that the reliability function, whether you find the reliability or probability of failure, I already said the same, because it's complement each other, is equal to 1 minus PF, and as we see there, this is equal to minus beta. Or, oh, I'm sorry, what am I doing? 1 minus phi minus beta. Or, in terms of R, I can say this is beta. Is it clear? Usually not clear. But if you look at this, you can say either way. I can say X. This is Fx. And if you look at the, this is phi, and if this guy will be minus beta, so this area is what? Probability of failure. This guy is probability of the failure. And this is phi, so this is really the symmetric, right? And mean is equal to 0, right? And standard deviation is equal to 1. So now this is a beta and all symmetric. I'm going to put this guy beta right here. If you look at the table shows, you know, from minus in, because of phi let's say x is equal to 2 pi e to the minus x over 2 square, right? Correct? If I say this is the, if this is a cumulative distribution function, then I can say this is from here to there, right? So I can say integration. So this is something like whatever. Why? This is what you do, right? This is integration up to the x, where we use minus beta. So I'm going to use beta here. This is a definition, standard, what do you call standard normal distribution function up to beta. So if you look at the table, you know, the range is up to beta, that's about all. So your idea is probability up to the the rest of the portion. This is what? That's the reliability, right? Because the whole thing is a 1. So rather than use a negative beta to get the reliability, I can just get all the way up to here, up to the beta. Then this is that portion. Look at this. This is that portion is equal to that portion, right? If you integrate up to the beta, then that's what the R is. Make sense? Really makes sense? That's why this is equal to the up to integration up to the beta, okay? Okay, now is whole idea is how we're gonna really get the MP point, the U star point. It has such a relation. So so next step, and which is really final step, is it up to here? Is it clear? Clear, right? It's to get all up to here. Very clear. Question? Q&A, questions? Yeah, I think if you read, as you read through the handout, should be all clear. That's nice part. There are a lot of still point which is not that good, but we'll see. Now is MPP search. MPP search by iterative approach using the recursive approach or formula. And which is God bless you, iteration approach. Update the current location. The idea is at the beginning you set the u vector. At 0 means its original, initial location. Initial location, you pick the initial, the u value. Then keep update. And keep update. Like usually at the beginning, if it's two-dimensional, I can say 0, 0, which is origin, which is not true, or starting point. Then U1, then UK, very general, then UK plus 1, and so on. Then as you keep looking, if this two value is close each other, for the norm of UK is UK plus 1. If the difference is less than or equal to the given epsilon, epsilon is some smallest value you want to set as acceptable criteria. So then iteration stops, then pick out maybe this value as a final value to use. Okay, that's what the iteration procedure. So again, back down to the same graph. I just erase U1, U2, and let's say this is the initial point, not the initial point, at the kth point. I'm going to say this is not the power kth iteration point from 0, 1, 2, and some kth point. If this is some kth point, then of course for the linear approximation using the two terms in the Taylor series, and I can draw this guy as like this. This is of course AK, which is outward direction from the G function, and this G function by the Taylor series expansion, this is G UK, of course, plus delta G UK is kth iteration point, and U minus UK transpose, which is not equal to 0 because it's in the iterative steps, so of course it's not yet equal to 0. If it's equal to 0 or close to 0, that's really close to MP point, okay? So it's not still 0. So next value you have to iterate. So just writing for that portion. Assume the k plus 1 point, let's say we hit the jackpot. Means right at that point we hit the MPP point, let's say. Okay. If you do that, then G U k plus 1, which is maybe another line I can draw here. let's say this is UK plus 1, and I can draw, of course, this line. Then you can, this is like, as I assume k plus 1 point is MPP point, if I draw this line, this should be, of course, beta k plus 1, but that's, let's say, final point. So if you do, this is equal to G UK plus, this is, I still should do this, delta G U updating, this is really updating, U K plus 1 minus UK transpose. And this is equal to, in this case, is equal to 0 because k plus 1 I said is MP point, okay? Remember here, what we formulate, one of the important equation is U star is minus beta A. So here I can say that UK kth U is equal to minus beta K, keep updating because this length is keep changing, because this location is keep updating at AK. If you look at carefully, usually what's happening is to get to next level, you have to use mostly use information at the K step. That's what's happening here. To get the update information, you use the previous information. So here, A K plus 1 step is not available. So you have to use, to get the UK plus 1, you have to use beta may available, as you would see, as A, K. A is anyway the unit vector. Its direction is, of course, could change it. But as we keep updating, we have to use information of A in the previous steps because it's not available, okay? Then if you do that, I think there's about, not that. See, screwed up here. No, this is correct. Beta is available this way. So if I rewrite here, AK, this is a unit vector of the gradient. So this is G U K and delta G U K. Then this is this is kth iteration point, but still unit vector. The pointing direction may not toward the origin, but that's very much improved, okay? So last iteration line is this. That's the iteration line. That's the iteration line. I'm going to write that equation here once again. G U K plus 1 is equal to G U K plus delta G K plus 1 minus UK T is equal to 0, because I said assume K plus 1 point is a MP point. So there, going to replace this guy as U K plus 1 is equal to minus beta K plus 1 times AK, replace it, and here we can replace UK is equal to minus beta K AK. No change on this in the K plus 1 step, but this is as usual. Then I want you to put these guys right in, put these guys right in there. And maybe we have a time to write this. If you do that, you have G UK, if you do, plus delta G UK AK transpose beta K minus beta K plus 1 is equal to 0. I want you to just to put that in, manipulate. Then this is equal to norm of GUK. Why? I'm going to just put that in, then I'm going to show you here. Back down here. AK, oops. This is reasoning why this is equal to this. But let's think a little bit. AK is a gradient over the norm of the gradient, right? It's a gradient, that would be the better way. AK is gradient at K step over the norm of A at K step, right? Then gradient vector times transpose of gradient vector is equal to norm square, right? Gradient vector times transpose of gradient vector of the norm is equal to square of the norm. Now clear? Okay, A vector times A is equal to A square, isn't it? Which is, this is vector times vector transpose, then that's a scalar. Scalar square. This is a scalar square. I have to put this guy maybe square. Make sense? Make sense? Then divided by what? A, right? Then this is equal to A. That's all I'm saying. So this guy becomes simply known. Okay. So then I can say that by looking at this guy is equal to this guy equal to 0, then you will get, to simplify it, this is equal to beta k plus g uk that. So you can update the beta. This is just a simplification of this guy. Okay. 1, 0, right? I'll stop right here, then we'll continue the Friday, then finishes up the procedure, then going to example problem. So the Friday, I want to go through, you solve the exam problem set. I assigned every problem to you, so when you come back, we'll finish the review, then I'll continue on this. So Yesu is okay, she's home? Okay, so 10:56, I'll see you Friday.